All right, let's apply the ratio test to a couple of problems to see how it works as well. And before we do that, I'll remind you, so the ratio test says that if you take the nth root of the nth term and let n go to infinity, then if you get some constant that is less than 1, then we conclude that this behaves like a geometric series with r less than 1, so it's a convergent and an absolutely convergent series. And if the ratio is greater than 1, then we have a divergent series. Okay? All right, so this first example is one where we actually could apply the ratio test as well, but let's try the root test instead. All right, and so what we're going to look at is the limit as n goes to infinity of the nth root of the absolute value of an. And so we can just evaluate that limit, and that's going to give us rho. And if you take an absolute value of something raised to the n, and assuming that thing is positive, you can that's equivalent to just taking the absolute value of the things inside. And so we can write this as limit n goes to infinity of 3 over n absolute value, which is, well, still 3 over n, all raised to the n. And then the nth root, remember, is just the 1 over nth power. It's another way of writing nth root. And so now we have just 3 over n to the n raised to the 1 over n. And when you have one power raised to another, you multiply the powers. And so we're left with just the limit as n goes to infinity of 3 over n to the 1, which is, of course, 0. And so since our ratio is less than 1, we would conclude that this is absolutely convergent. Okay, let's try another one. Let's look at the sum of, how about, this is number 40 from the book, 1 plus 1 over n raised to the negative n power. And this is actually a limit that's quite tricky to evaluate. You would need to do clever tricks involving logarithms to actually even apply the nth term test to this. But what we'll see is that because we have our term is just something raised to the nth power, this is going to be not so bad to evaluate using the root test. So we'll look at the limit as n goes to infinity of the nth root of the absolute value of 1 plus 1 over n to the negative n. Okay, again, everything is positive here, so we don't need the absolute values. And so we can write this as the limit as n goes to infinity of 1 plus 1 over n raised to the negative n raised to the 1 over n, because the nth root is just 1 over n, which is, let's see, if you multiply the exponents, we're going to be left with limit as n goes to infinity of 1 plus 1 over n to the negative 1, which is equivalent to limit as n goes to infinity of 1 over 1 plus 1 over n, which is just 1. Well, if rho is 1, remember that both the ratio and the root tests are inconclusive. So this is inconclusive here. Well, that's unfortunate. So this limit wasn't so bad, but it turns out we are actually going to need to try another technique. And so let's try the nth term test. Let's take the limit as n goes to infinity of 1 plus 1 over n raised to the negative n. And let's call that quantity, I'll call it L. And to make life easy, I'm going to take a log of both sides of this equation. And so I'll have the log of the limit and that's got to be equal to the log of L. All right, now the reason for this is the log is going to help us deal with this exponent of negative L. And so let's just remember that in the end, what we're going to get when we take our limit is not L, but rather the log of the thing that we're actually interested in. And so one thing that we can do is we can bring the log inside, since it doesn't depend on n. And so we'll have the limit, again, this is log L, is the limit as n goes to infinity of the log of 1 plus 1 over n to the negative n. And now that we have the log inside, the negative n exponent inside of the logarithm can be brought out front. That's one of our log properties. And so we'll get let's see, negative n times the log of 1 plus 1 over n. And, well, as n goes to infinity, what happens to that? Well, this first term wants to go to infinity, and this other term wants to go to 1 plus 0, so log of 1, which is 0. Well, that's indeterminate. But what we can do is we can write this as log 1 plus 1 over n over 1 over n. And you can check that's multiplying by n is the same thing as dividing by 1 over n. And now we have infinity. Let's see, the numerator wants to approach 0. The denominator wants to approach 0. And so this is a situation where L'Hopital's rule could be used, in which case we'll take derivative of the top, which would be negative. Derivative of a log is 1 over what's inside. But then we have to multiply by the derivative of what's inside. And then in the bottom, we'll have derivative of 1 over n. And I'm not evaluating that because, notice, derivative of 1 plus 1 over n is the same thing as the derivative of 1 over n, since its derivative is 0. So actually, we don't even have to evaluate those derivatives because they're just going to cancel each other out. And we'll be left with limit as n goes to infinity of negative 1 over 1 plus 1 over n, which is just going to be negative 1. Okay? So the log of L is negative 1. It's the log of the thing that we actually wanted to find, which is we were looking at the nth term test to determine what the terms approached. What that means is L is equal to e to the negative 1, which is the same thing as 1 over e. And 1 over e is 1 divided by somewhere around 2.7. So that's some number that's roughly a third. But remember what the nth term test says. It says that if the terms approach anything other than 0, the series diverges. And in this case, we see that the terms approach 1 over e. And so we would conclude that this is a divergent series. Terms do not approach 0. Okay? So sometimes you're going to apply the nth term, the ratio test or the root test and get 1. And in that case, you're going to have to go with another test. The nth term test is often a good candidate for that, or sometimes an integral test or p-series would be worth considering at that point. All right, let's do one last example. Let's try, how about number 38, which is the sum from k equals 0 to infinity of k over k plus 10 to the k. Actually, I'm going to change that. Let's make that a k squared. All right. All right, so this is a modification of a book problem. All right, so let's look at that one. And we'll again look at the limit as n goes to infinity of the nth root of the absolute value of an. In this case, again, our terms are positive, so we don't really need to worry about the absolute values. There are cases where that would be important, because otherwise you might be taking a root of a negative number, which may not exist. But in this case, we don't need absolute values. What we do have is, well, if ak is k squared over k plus 10 to the k, then an would be equal to n squared over n plus 10 all to the n. And we want to take the nth root of that, which is the same thing as raising it to the 1 over n power. And so we're going to be left with a limit as n goes to infinity of n squared over n plus 10, since the 1 over n, the nth root part, will cancel the n. And it doesn't take a whole lot of work. L'Hopital's rule would be appropriate here, or multiplying by 1 over n on top and bottom to show that that is equal to infinity. And that means that we have rho greater than 1, so we have a divergent series. All right, so those are 3 examples with the root test.